Deep reinforcement learning agents have graduated from closed video game simulations. They are now operating at scale in high-stakes environments. These algorithms act as primary gatekeepers for core societal functions, making automated decisions about who gets a mortgage, who is shortlisted for a job, and who is granted parole. In response to this shift, the European Union established a baseline for AI governance through its high-level expert group. This framework dictates that any deployed AI must hit three non-negotiable targets. It must be lawful, it must be ethical, and it must be robust. We know how to define lawful through legislation and robust through engineering stress tests. Ethical AI presents a profound engineering paradox because human ethics lack a universal mathematical definition. When policy experts draft ethical guidelines, they use language built for human interpretation. Engineers have to write code built on strict logic. To make an algorithm fair, an engineer has to translate an abstract social policy into a rigid mathematical constraint. Doing so forces a strict trade-off between outcome parity, predictive accuracy, and excess risk. You can see this tension mapped directly onto the EU's Trustworthy AI framework. When you look at the 7 key requirements, you find competing mandates. Implementing diversity, non-discrimination, and fairness directly clashes with maximizing technical robustness and safety. Achieving trustworthy AI is not about finding mathematical perfection. It requires engineering a system that successfully balances these conflicting technical constraints. The tech industry often treats AI bias as a data quality issue, a simple case of garbage in, garbage out. Algorithms learn from historical data. That data is already shaped by decades of exclusion and inequality. Through the amplification effect, algorithms actively scale up and intensify those existing inequalities. If a recruitment tool detects a slight historical preference for male candidates, the optimization process will latch onto that pattern and systematically filter out female applicants across millions of automated decisions. The standard industry fix is to collect a perfectly balanced, diverse dataset. That step is necessary, but mathematically insufficient. A model trained on perfectly balanced data can still produce discriminatory outcomes due to blind spots in the training process itself. Engineers have to move beyond simple data scrubbing. They must implement structural interventions within the algorithm's architecture to enforce fairness. Before intervening in the architecture, engineers must choose a mathematical definition of fairness. These definitions fundamentally conflict. The first metric is statistical parity, which focuses exclusively on outcome equality. This is where we get the 4/5 rule, stating the ratio of positive outcomes for a protected group compared to an advantaged group must be at least 0.8. This rule forces the algorithm to approve candidates from different demographic groups at roughly the same rate. The conflicting second metric is equalized odds. This ignores overall outcomes and demands accuracy parity. It requires the true positive and false positive rates to be identical across different demographic groups. This creates a mathematical contradiction. It is impossible to guarantee equal outcomes if the baseline accuracy rates differ between groups in reality.
A third metric is counterfactual fairness. This uses causal reasoning. It requires a prediction to remain identical if you flip only the demographic attribute in a hypothetical scenario, keeping everything else equal. Achieving perfect counterfactual fairness requires extreme causal isolation, which heavily degrades the model's ability to learn from its environment. Because these mathematical states are mutually exclusive, choosing a fairness metric means actively choosing which type of bias you are willing to allow. To enforce these metrics, engineers use 3 distinct structural interventions in the machine learning pipeline. Stage 1 is pre-processing, which happens before model training begins. Here, engineers use data reweighting to manually balance class distributions, assigning varying multipliers to data points from underrepresented groups. Stage 2 is in-processing. This adjusts the model architecture itself during training. Engineers modify the loss function here to incorporate fairness considerations. If the algorithm starts skilling its results, a mathematical fairness penalty dynamically corrects it during the training loop. Stage 3 is post-processing. The model is already trained, and engineers are intervening in the final outputs. They calibrate the outputs by adjusting decision thresholds. They draw different boundaries for different demographic groups to force equal opportunity across the board. Applying interventions across all three stages allows engineers to tune a model, but it forces them to decide how far to push these limits before breaking the model's primary function. 2025 research from Xylos identifies exactly what happens when you apply these structural mitigations too aggressively. You hit the convex Pareto frontier. This is the strict mathematical boundary where a system cannot be made fairer without losing accuracy.
Enforcing fairness constraints, like pushing a model toward perfect counterfactual fairness, forces it down this curve, incurring severe excess risk. That excess risk translates into the real world, reducing lender profitability and lowering hiring system efficiency. Because a protected demographic attribute can usually be inferred from other features in the data, this trade-off is virtually inescapable. The Pareto frontier proves mathematically that a perfectly fair and perfectly accurate model is a fiction. Engineering an AI system means finding the optimal point of compromise. The EU framework requires organizations to manage this point of compromise in production. This assessment layer is operationalized through continuous auditing. Data scientists rely on open-source toolkits like IBM AI Fairness 360 and Google's What If tool. They track over 70 metrics to catch bias drift, inequities emerging after the model is deployed. By 2026, the industry has reached a clear consensus. Reductionistic mathematical representations of fairness bear little resemblance to real-life context. The root problem of bias is human. Algorithmic fairness tools are necessary, but they are insufficient without human judgment guiding the parameters. Until we build fairer systems for defining and rewarding talent, algorithms will simply mirror the inequities we have yet to correct. The ultimate goal is not mathematically flawless AI. It is the engineering of transparent, auditable socio-technical systems that systematically minimize harm.